Hello, in this video I'm going to solve the following problem for you. The subject is topology and the topic is topological spaces. Let X be an infinite set. Is tau equals to the set consisting of all subsets U of X such that either U is equal to X or X minus U is infinite, a topology on X? Motivate your answer. Okay, I want to show you by bringing counterexample that no, tau is not a topology on X in general. And I think it would be good if I can bring you two different types of counterexamples that one can think in this problem. And I want to show that by my counterexample that this tau is not necessarily closed under arbitrary unions, which is of course one of the axioms that should be met by a topology. Okay, so I want to show that this tau is not closed under arbitrary unions, and I want to provide you with two different counterexamples. Okay, so the first counterexample that I want to show for you is that let us say that X is this infinite set, because I have to respect my X should be an infinite set. So I will consider this interval as my X. 0 is excluded, 1 is included. So if you want to draw a diagram for it, so this is my axis of R, and then here 0 is excluded, but 1 here is included. So this set is my X. Clearly this set is infinite. Now I would say that if n belongs to n, define un to be the interval, the open interval from 0 up to 1 minus 1 over 1 plus n. Okay, so if you want to get a feeling how this interval looks like, it starts again from 0, of course excluding 0, but it goes up to 1 minus a positive number. So I would say, for example, you can imagine 1 minus 1 over 1 plus n is somewhere here. It is smaller than 1. And if n becomes larger and larger, this point becomes closer and closer to 1. But of course, this is also excluded. So let me put a hollow circle here. So if I want you to see, this is what I am considering to be un. Okay? Now, my claim is that all these UNs belong to tau. Okay? In order to show that UN belong to tau, I have to show that UN is a subset of this set, which of course it is. And I should show that either it is equal to X, which of course is not, or its complement is infinite. So what is the complement of un? So x minus un is this interval minus that interval for any natural number n, yes? And of course, it's extremely simple to see from this picture that this will be the closed interval from 1 minus 1 over 1 plus n up to 1 itself, yes? So this part will be x minus un, but because the end point is excluded from the set itself, it should be included in its complement. So that will be x minus un. What type of set is this? Is infinite. Okay? So I was able to show that for any choice of n, x minus un is an infinite set. So this means that un belongs to tau. So for all n in n, un belongs to tau. Okay? So now consider the union of all these UNs where n belongs to n. Okay? This is very simple to show that if you do the calculations, it is very easy to convince yourself of it. N belongs to n. What happens? When n increases, this point is fixed for this interval, but when n increases, this becomes closer and closer, to 1, but it will never be equal to 1. So this is very simple to show that this becomes the open interval from 0 to 1. But now my claim is that this union does not belong to tau. Okay? If this union is going to be in tau, it should be either equal to x itself, which of course is not, because this is the open interval, but here this is closed. Or its difference should be infinite, but the difference is also, the complement should also be infinite, but this is not the case. Why? Because if I calculate the complement of this union, this becomes 0, 1 minus 0, 1, which will be a singleton set, is not infinite. So this means that the union un, n belongs to n, does not belong to tau. So I was able to bring a collection of sets in tau for which the union is not in tau. So this shows that no, tau is not a topology. Okay? So the problem is finished here. But if you want, we can also have another counterexample, which is also nice to see. Okay, for another counterexample, I would say that let x be an arbitrary element of x. Okay, the set ux, defined to be the singleton consisting of only x, is in tau. Yes, why is that? Because, first of all, x is an infinite set, any set that you want to. So I am not giving an example for x. X is any infinite set, and I am picking any element little x from it, and I construct a singleton by that element. I am claiming that this singleton is definitely in tau. To show that this singleton is tau, I have to show that this is a subset of x, which of course is, because x is chosen from capital X. Then I have to show either it is equal to x, which is in this case not correct, or I have to show that its complement is infinite, which is also the case. Why? Because x minus ux, x is infinite, ux is singleton, so if I find the complement is infinite. So this means that this belongs to tau. So this means that ux belongs to tau. Yes? Okay, but now what I say, let x naught be a fixed element of x. Now I define this collection for you. Consider the collection consisting of all ux's, so that x belongs to x, but x is not equal to that fixed element. Okay? So this is a collection of sets from tau. Now what I want to do, I want to union all of them. So union of ux, where x belongs to x, but x is not equal to x naught. This is a union. I'm claiming that this union does not belong to tau, even though each one of the elements of the collection belongs to tau. Okay, why is that? That is very simple. If I ask you what is the answer to this, so what you are doing, you are unioning all singletons of set capital X except one single one of them. So it is very simple to see. This is just nothing except x itself minus that particular element. Yes? Okay, but is this in my tau? No, because first of all, it is not equal to x, and its complement is the singleton x itself is not infinite. So this means that the union ux, x belongs to x, x is not equal to x naught, does not belong to tau. Okay, so here this is also a good counterexample because it doesn't assume anything about the structure of this set X. You see, in the first example, I assumed that this is the form of this infinite set, and of course I was able to do that, but for this case I'm not assuming anything about the structure of the set X. I'm just assuming that X is infinite, and I just showed that even without assuming anything about the structure of the set itself, still you can show that this is not closed under arbitrary unions. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.